Hi guys. Uh, Today we're talking about the optic flow concept. I hope everybody is fine. First of all, I wish good luck to everyone, your families. Let me go over the outline of optic flow. In vision, we are right now in the mid-level part, which I mean starting from very fundamentals, image formation, or color, or um some other basic concepts. Now that we move to feature extraction for images, that's a mid-level process. And for video, we can assume this fundamental information, which is the temporal change, is basically represented by something called optic flow. We will see some different approaches. Now let's start. Okay, optic flow is first of all the apparent motion of the brightness pattern. In other words, we watch a video which is changing in time, the intensities, and optic flow is their apparent change. Okay, motion field is the real 3D motion of the objects which is projected on the images. Ideally, they should be equivalent to each other. The projected 2D motion field and the optic flow, the displacements of the intensities. But there could be many reasons, like there is a Lambertian ball and it's moving. It has a real 2D motion field at the end. But when the light source don't move any changes, you will not see any brightness, apparent brightness change. Therefore, we call it zero optic flow. Just here, maybe the ball is moving, but the intensities are always constant because the distant point source, which is sitting here, and the normal vectors are always constant, and the angle between the normal vectors and the intensity direction is constant. Therefore, due to Lambertian's law, you see nothing else. It could be the other way around as well. Okay, we can have the non-zero motion, the zero motion field. The ball is not moving, but for example, the light source is moving. Then you will see something like this from this T1 to T2. When it's moving like that, obviously the intensities change. There will be something in the optic flow. The brightness patterns are moving, but obviously the object is not moving anywhere. Therefore, this is the famous Barber's pole. When the real object is, the real motion is rotating in 3D, but once you see is basically the red strip is going translationally upwards. That's again from optic flow. It's a translating motion going upwards, but the real motion field should be something rotating maybe. Okay, now this is the only observation about object motion, okay, and optic flow. And what we are trying to do is we are trying to estimate from the intensities, okay. Now, at this point, we will assume typically or mostly the optic flow and the motion field are equal to each other. We will estimate the optic flow from intensities, and we will assume that that will be equal to motion field. Okay, let's move how to estimate it. Let's E depends the irradiance, the pixel, the photon power on the sensor, x, y, t. Not only the special coordinates x and y. Now this time there is at time t. The image point is x and y. Now there is two unknowns, u and v, x, y, the horizontal and vertical components of the optic flow field. And what we are having is we are assuming the image radiance to be the same at the next time instant. Therefore, we will say that the light photons coming to the same point at the same next time instant will be the same. Hence, this is the fundamental assumption that we will make. In other words, there's an object intensity at x and y at time t is equal to E, okay? This is something radiating from the object. The object moves to, at the next frame, t plus delta t goes to the u delta t horizontal displacement and v delta t as vertical displacement. It moves to these positions, and that power and this power between two time frame instants at these two time locations should be constant. Otherwise, we will unable to estimate anything. Okay, therefore, this is our fundamental assumption where we will say that that will stay as constant. Okay, now this single constraint is not sufficient to determine both u and v because there are two unknowns and we are having a single equation. It's a nonlinear equation. Please note the unknowns are inside the independent variables of the function. Okay, therefore this is a single constraint, not sufficient and also nonlinear. Now the trick is the motion field, the unknown u and v, is typically continuous for many objects around us. Therefore, we can make a Taylor series expansion for this function here around x and y point. We can open linearize it around x and y. Once we do it, the result becomes this is the function at these 3 points, and we are just writing that x, y, t around this point. In special temporal volume, we are just writing the expansion. 3 first order terms, horizontal component of the intensity is vertical component, and the time derivative. Please note this time derivative is nothing but time difference, intensity change divided by the time difference, and multiplying with delta x, delta y, delta t, plus the higher order terms. And this point, this part, these two equations, left hand side and right hand side, is equal to nothing but mathematical Taylor series expansion. But that should be equal to E of x, y, t due to this assumption that we are saying. In other words, objects don't change their intensities during their motions. Now, please note there are these two terms on the left hand side, right hand side equal to each other. We just drop them. And we will just obtain nothing but a single term, nothing but this one. Okay? Therefore, we are having right now this relation, which is the horizontal derivative of the intensities. Now, instead of delta y, I can write, if I just divide both left hand side and right hand side by delta t, delta x over delta t is nothing but the velocity of the pixel, horizontal component, and the vertical component, and then delta t is cancelled out. The last term will be nothing but the time derivative of the image brightness. That's equal to 0. This is called the optical flow constraint equation. That's the single equation, unfortunately with two unknowns, and these two unknowns are our optical flow horizontal and vertical components u and v. For every pixel, u and v could change. We don't know that. And this single equation with two unknowns, obviously, we cannot solve it at this point. But that gives us an idea how the spatiotemporal derivatives of the intensities and horizontal and the vertical components of the pixel velocities are basically related to each other. Now, let's go to the next step. Just try to understand it better. Let's make it more simple. Let's assume a one-dimensional image, like a line image, only with respect to x is changing, and obviously there is time constraint at like different frames in time. The previous equation that we have, the time derivative is nothing but, let's assume 0 and 1. Okay, we have 0 and 1. Therefore, the time derivative can be assumed nothing but this difference here. Okay, the next one subtracted from here, there is a minus because it should be typically the way around. Okay, now this is equal to, this is obtained through just the previous equation that we have. Okay, the previous equation that we have here, just one dimensional, this term is gone. E of x u plus E of t is equal to 0. Let's put this to the other side. E of x u is equal to minus E of t. Just divide by u, we obtain nothing but this relation here. And now this relation is our fundamental thing that we can have. Okay, this is the optic flow equation. And if you visualize it, just please note this is our, at time 0, our intensity change with respect to x. This is the first frame, and the first frame intensity is from this x point to that x point. It's increasing, it's getting brighter and brighter, just a slow ramp, intensity ramp here. It's moving in the next time instant. Due to motion, this point moves to here, that point moves to there. Now, the whole equation here, let's visualize in this point. The unknown is u. How much did we move from here to here? Okay, this is unknown to us. We are trying to estimate a single unknown, a single equation, obviously here. And now this is the time difference that we are talking about. We are just subtracting. We are just subtracting this one from that one, the next one from the other one. Therefore, we have this kind of a relation here. Please note this slope is known to us because this slope is nothing but our horizontal intensity derivative that we have learned in the previous chapter. Therefore, this slope is Ex. And that difference here, that arrow is nothing but time difference. Therefore, this is the unknown. Therefore, we have to be able to obtain this unknown in this one-dimensional case. Okay, therefore, what we are obtaining here is nothing but this 1D relation is simply giving us, knowing this time derivative, the intensity difference between this point and that point coming to the same x point, okay? This is the time derivative of x of the intensities. This is the unknown u, and this slope is given to us. Therefore, this unknown displacement can be obtained through such a relation, okay? But this is only for 1D. Applicable in 2 dimensions, unfortunately 2 unknowns, but still there could be a way of solving this problem. Okay, the OpticalFlow constraint equation, just let's note one more thing. Let's assume u and v is a vector, the unknown horizontal displacement of a pixel, and this is the current intensity of the same pixel. We understand that their dot product, their inner product, should be equal to minus time derivative. Okay, this is our fundamental equation right now. Here, what we are having is this. If we draw this in the UV plane, okay, in the UV plane, what we are having is nothing but an EX-EY vector, okay, and this EX-EY vector is basically inner product with a UV vector, and that inner product is giving you minus ET. Now, what is this inner product? This inner product is in fact, nothing but, for example, projection of this one to here or the projection of this one to here. Therefore, if we think about our unknown UV having 2 components, sum of 2 vectors, one in the direction of the intensity gradient. Okay, you have a pixel object point. It has an independent intensity gradient. This gradient is like that, and it has also an independent motion of the object. It could be arbitrary, but if we can write this OpticalFlow in terms of 2 components, one in the direction, one in the perpendicular direction, okay? Therefore, these are one component along the brightness gradient, one component perpendicular to the brightness gradient. Now, the concept is the component perpendicular to the gradient. In other words, assume that's an arbitrary UV here. The component which is perpendicular in this direction, their inner product is equal to 0. It cannot create any difference of the intensities in time. This is called the aperture problem, okay? We only observe the component in the direction of the brightness gradient, okay? And this is nothing but, if you take the inner product, and this is the normal vector of your nx, and the n vector, which is in the direction of brightness gradient, this inner product can be written like this, the intensity gradient, and this inner product is minus ET. And if you look at here, this is an arbitrary UMV. This is this component in the direction along the gradient. This is in the direction which is perpendicular to the gradient, and we only see this component. The other component simply is invisible to us. Now, very simple example how this is possible. Do you see any object motion here? Okay, If you look at here, there is no more object motion. In fact, there is something moving. If we just remove the, this should be supposedly, it's an animated GIF, it's going back and forth in this direction. Now, if you move in this direction, back and forth, you see this, there is the intensity gradient in this direction of this red arrow. Everywhere is constant, but along these peripherals, the edges, we have the intensity gradient here and there. Unfortunately, the intensity gradient here showing the north and the motion between east-west, they are perpendicular, and therefore we don't see anything here. This is called the aperture problem. Therefore we can only observe through optic flow only the component of the object motion along the direction of the brightness gradient. We cannot observe the component perpendicular to the object gradient. Let's estimate motion. We only say that it is difficult to estimate single equation, two unknowns. Therefore, let's see how we can estimate. In fact, the remaining part of this chapter is showing us, it will show us how to estimate this thing from brightness variation and of the object motion. A group of methods called gradient-based methods, using the special temporal gradients. It was basically based on the optic flow techniques. Okay. Therefore, optic flow solution. I'm gonna show how it is obtained, the ill-posedness of this problem. How can we basically approach the problem? There is also PAL recursive algorithms. Again, trying to minimize displaced frame difference by making an optimization, gradient descent optimization, and finding the displacement field as a gradient descent, which is minimizing the displaced frame differences. I'm not going to show this, it is very relevant to the previous one. Okay. Another base technique is the correspondence-based techniques, matching type methods. This is based on the ideas that we have seen before, which is basically we see that we are able to obtain corners or blobs, some features in the previous chapter. You can find these things, you can match them through some descriptors, and basically you find some sparse methods where sparse points can be matched between frames. Okay, now the fundamental techniques are block and region-based methods. Instead of features, just use a block as a to be matched in the next frame. Okay, or you can make edge corner blob matching. There is also another group of techniques. Until now, all pixels of an image independently estimated. Their optic flow solutions can be independently estimated. The parametric methods assume the motion vectors, the optic flow of a group of pixels, of a region of pixels, maybe the whole image, is matching a parametric form. Okay, therefore this parametric form could be different. Okay, let's see. This is the parametric form. It could be affine. Okay, it could be perspective. Please note there are x and y is at one time instance the t1 you have xy. The same point goes to x prime, y prime, and all the motion vectors in a region obeys these 6 parameters that we have: a0, a1, a2, a3, a4, a5. Therefore, we are just enforcing only 6 parameters, but obeying such a parametric form between the positions. Or more complicated, like perspective, where x prime is a rational polynomial, first order polynomial. Okay, we have the y prime is also in the same way. And finally, we will see frequency-based techniques. In fact, I'm gonna extend these things with some other recent new concepts. Now let's start with the first approach. In other words, optic flow, a single equation with 2 unknowns. How can I solve it? Okay, now we have to put an extra constraint. It could be a rigid body assumption. Later we will see in 3D, we will see these concepts. We can say that, hey, the motion vectors uv for a point and its neighbors should be slowly changing because typically objects around us do a similar motion. Therefore, we can say that the horizontal and vertical derivatives of the horizontal component and the vertical components should be very small. In other words, from pixel to pixel, the u value should not change abruptly, except for the object boundaries, obviously. If we try to minimize such a term, the square of the horizontal component of the horizontal and vice versa, if we try to minimize this, that will bring us an extra constraint which will help us to solve the unknown u and v for every point. Now, what is the other constraint that we can use? Obviously, the optic flow error. Therefore, ideally, u of xu and e of xu and e of yv plus et squared should be equal to 0 for every pixel. Please note these integrals. It's like a continuous image. It is basically for every pixel you are calculating the horizontal and the vertical intensity gradients, time intensity gradients. Then for every pixel there is an unknown UV. In other words, if you have a 1 million pixel image, 1 million, 2 million unknowns, 1 million U, 1 million V, and I'm saying that U and V satisfy at every pixel this, their sum should be minimized. In the same time, the neighboring UMVs also should be very similar to each other. Now, this is the smoothness of the optic flow, one approach that we can move forward. Okay, now if we look at here, we can just write these things and we try to minimize them together. Okay, like two term optimization, ES just be minimized, EC also be minimized, like an apple and peach. We are just waiting with lambda, and we will try to minimize these equations together for every pixel horizontal vertical components. You can do it in discrete time, obviously, okay, because this is an continuous right now. Let's do it in the same concepts in discrete time. This is the optic flow equation. Uij and Vij, our optic flow components of the lattice on the image for every ij point. Their square sum is this. If you sum them for every ij, you are basically minimizing this. Please note, ui, uj, for every pixel we have two unknowns. And there is the next term, which is a horizontal derivative approximation of the horizontal component and the vertical component, okay? I plus 1 I, j plus 1 j. If you just subtract these two, these are neighboring horizontal components. These are neighboring vertical components, okay, of the horizontal field. Similarly for vertical field, if you just also sum a square, and if you just sum for every pixel, you will obtain in the ideal case, optimal case, that E should be a minimum. Now, differentiating this E with respect to UKL and VKL, we can obtain this result. Now, in the first look, it's like complicated, but let's look at carefully. Starting from here, if we take the derivative of this term with respect to UKL, please note this is for every pixel that you are doing, and only one of them, KL position, we are taking the derivative. UKL will bring this 2 here, okay? EX will go out, this EX here, okay? And nothing but this term without a square. And similarly for Y. Now, this is the tricky part. Please note, in the image, I am trying to take the derivative of a very specific single point, KL. Let's assume KL is this point, this corner here. Therefore, this UKL will be inside this term for such a summation. Once you are doing a difference between these two, okay, then the other two. Therefore, we will have two terms. UKL is coming into the picture. Similarly, UKL will be in the picture here as well, again. Therefore, what we are having is, for a point KL, we have to have the four corners, four neighbors, will be in the derivatives appropriately, and therefore this Sij, the derivative with respect to UKL, will bring us UKL subtracted with the 4 local neighbor average, okay, due to these terms here. Obviously these are constant, they will drop for UKL derivatives. And VKL will bring this one. And if we equate them to 0, okay, if we equate them to 0, we will obtain this relation. Therefore, just equating them to 0 and put the unknown UKL to the left hand side, all the terms, this term, okay, it will be here. EX square lambda, it's here. And the 2's, I just drop the 2's everywhere. It's equal to 0 because, okay. And VKL terms here, okay, the VKL terms are here. EX, EY will be here. And on the right hand side, this term, okay, we will put to the other side. And finally, this term ETEX, independent of U and V, will be on the right hand side. Now we have equations. The left hand side, unknown UKL, VKL. Right hand side, this is known. We know the spatiotemporal derivatives of the pixel, but this is unknown because we don't know anything about our any neighbors. We don't know any motion vector, but let's assume they are known until at this point. That will be an iterative equation because, okay. Now from these equations, okay, Horn and Shang in 81 solved these things, okay, and just put this equation, this 2 by 2 matrix here, which is UKL, VKL vector is multiplied with 2 by 2 matrix. Take the inverse of the matrix to the other side, and just you will obtain nothing but this simple solution. Now, obviously, this is with respect to an iteration n, and for different iterations, starting from an initial arbitrary estimate, we just basically making an iterative updates, and those updates are giving us the next solutions. Therefore, as soon as you obtain the next solutions for U and V, you insert them back to here. And you go to the next solution. Now, let's look at the equations. Although from this a simple 2 by 2 matrix inverse, you got this result. In the numerator, this is nothing but our OpticalFlow evaluated as the average of your 4 neighbors. Okay? This is your OpticalFlow equation averaged by your 4 neighbors. If the average of your 4 neighbors satisfying the OpticalFlow at this point, that term will be 0. Okay, that term will be 0. There will be no update with respect to x. Or vice versa, the term, if this is the same term is also equal to 0, you will not then update here as well. Okay, therefore the update here is due to this adjustment factor, which is equal on both parts. And let's see what is here. We are having the updates as a scalar, this adjustment factor is scalar, multiplying EX and EY. Hey, our updates are only in the direction of the gradient. EX and EY multiply with the same constant. In other words, EX, EY vector is multiplying with a constant, okay? And that you are adding on top of our previous values. Therefore, what we are learning is this. Like the aperture problem, we only make updates along the intensity direction gradient, okay? This is nothing but this. And this update is like the terms which are not satisfying the OpticalFlow equation here with your average vectors, okay? And the adjustment factor is becoming smaller if you have an intensity gradient. Large, if it is small, then we will have a much larger update. That term becoming 0 or equal to 1, you will have a larger update here. Okay, this is our iterative solution, famous Horn and Shang solution of the OpticalFlow. For every pixel, starting from arbitrary values, we were able to obtain some result, and those updates, as I have said before, in the direction of the EX-EY. Now, we have to calculate, the only thing we have to calculate is the horizontal, vertical, and the time derivatives. Okay, you can have such a cube, x, y, and this is the t direction, 2 by 2. Therefore, the time derivatives, for example, the horizontal derivatives, the difference between these two, the difference between the, sorry, for horizontal derivatives, the difference between these two, these two, these two, and those two, 4 terms averaged. This is the thing we have did before. And time derivative, maybe the time derivative will be these differences, and these differences, and their averages. Okay, for average. Now, another thing is, as we did before, fitting a spatiotemporal surface to those 8 intensities, like this function here, and taking the explicit derivatives, time derivative or horizontal, vertical derivatives here, could be a better approach. In other words, from 8 intensities we find these parameters, okay, and then we will just simply fit EXAY a parametric form, and this parametric form will give us these partial derivatives in a closed form expression. Okay, that's the OpticalFlow Horn and Shank. We have the discontinuities in the OpticalFlow because everything was saying that it's a smoothness assumption. This is only true for accept the boundaries. For translating rigid bodies inside the rigid bodies, that could be true. For the rotating bodies, it could also be true, the smoothness assumption, slightly any kind of rotation around the optical axis or around the object. Still, the neighboring optic flow vectors will be very similar. The elastic non-rigid objects could also be true. But at the object boundaries, obviously, when there is an object moving, the boundaries of the object, the optic flow equation will no more work. Your neighboring motion vector will be a constant background while you are moving. Therefore, the optic flow equation is only true inside the boundaries. Okay. Therefore, if your boundaries are known, your optic flow estimation could be better reliably obtained. But to tell the truth, it's a chicken egg problem because at the end, the boundaries can be obtained through motion vectors, but the motion vectors cannot be obtained from the nothing but the motion vectors. Therefore, the boundary and the motion vectors, it's a chicken egg problem. Typically, people are iteratively solved. Once you go to any kind of intensity boundary, you basically stop your smoothness assumption, okay, because at that point you know that there will be no more such an intensity boundary, there should be no more smoothing. This is a directional smoothness constraint. Okay, now let me go to another technique other than this Horn and Shank fundamental technique. Let's remember the previous technique. The previous technique was finding an iterative, obviously suboptimal solution, and it gives for every pixel point an UMV vector. That's too much. 1 million pixels, you have 2 million estimates. Starting from an arbitrary field, because iteratively you need that, but you give at the end a dense solution. The next solution I'm going to show you, called Canada-Lucas tracker, is somewhat different. It is basically tries to solve the same results at some sparse points, okay? But it gives a more reliable answer. Now, how does it work? Let's see how does it work. Let's see, yeah. Now, the concept is we are assuming this time a stronger assumption. Within a region B, a block B, I'm gonna say the U vector, U and V vector is constant. It's unchanged. Previously I was saying smooth. This time hard constraint, constant. Now if you put this constraint, if you solve the optic flow equation, if you minimize the optic flow equation here, okay, we will see this result, okay, which is basically giving us this result, and that result is saying inside the region B for ij pixels, the optical flow constraint equation, first derivative, horizontal, vertical, and time derivative, this equation squared should be a minimum. It should be a minimum, and you have to find u and v, which is minimizing this inside this region B. Okay, how can you achieve this? There are two unknowns, and let's have this equation here. Okay, let's have the equation here, and let's go to the taking the derivative of this with respect to u and with respect to v and equate to 0. Again, if you take the derivative of this thing with respect to u, 2 will go down, and it's homogeneous, it goes out. Ex will go out, this is the ex due to this, and nothing but this thing equal to 0. And similarly, we have ey and the other equation with respect to v. Now, the optic flow equation inside this block will be obtained in this way. Okay? Therefore, if you just write these equations, this time u and v, there is nothing like a nonlinear equation as before. We will have all the terms u and v. This is a 2 by 2 matrix inside here. Ex, this is this term. It's sum of every term inside B. Please note, inside B, this EXIJ is not constant. Maybe if there are 9, it's a 3 by 3 region. There are 9 different EXE and EY and EXEY values. Okay? Therefore, we are having here this thing is obviously not constant, and you are summing these things. This is the square of EX, square of EY, EXEY, and this is this 2 by 2 matrix is inverse, and put it this side, multiply with ETEX, this term, which is already put it to the other side as minus, and ETEY here as minus, and this is your solution. Hey, now this time we are able to find the solution by the assumption that within a region, a huge region B, maybe 9 pixels, 10 pixels, 100 pixels, we assume u and v only a single constant value. Now, the question is it easy to take the inverse of this? Is this inverse always exist? Well, if you look at here, if you have an homogeneous region, we will see that that will be 0, those will be 0, and you will have a singular matrix, and you cannot obtain its inverse. As long as this 2 by 2 matrix has an inverse, we could have this thing, this KLT solution, Canada-Lucas solution, can be obtained just obtaining the inverse of this 2 by 2 matrix. And the reason, or the case when this is non-singular, is once we have a corner. If we remember the Harris corner criteria, you will see that when you have two eigenvalues, lambda 1 and lambda 2, both of them non-zero, which is applicable and in the corners, at those corners we could have two high lambda values. The determinant is non-zero, therefore this is non-singular, and we can put the inverse to the other side. Therefore, the moral of the story is this: we could have a solution only at the pixel points where this previously called C matrix in Harris corner detector, this matrix has two large eigenvalues which means the determinant is non-zero. Okay? Therefore, for the corner points, for the sparse corner points, Canada-Lucas tracker gives you a very reliable motion vector estimate, optic flow estimate. Let's try to understand the optic flow better. Unfortunately, if you just simply implement our Canada-Lucas tracker in this naive way, just taking this inverse just as a single value, sometimes the results are not very precise. We have already seen this concept. This is IU at time is equal to U, one intensity profile, one dimensional. This is IV, which is the other thing that we are obtaining in the second one. Okay? And for these two intensity profiles that we have a motion in between. This is unknown to us. Now, please note these are our intensity derivatives. Okay, this is our intensity derivative. This little tangent here is intensity derivative, horizontal intensity derivative at this point, and this EI is nothing but our time derivative. Now, let's see how do we estimate it in a more precise manner. I am obtaining a displacement after every KLT inversion. In other words, just look at the previous thing here. Here we have an estimate between two frames, and for the pixel at ij we have an estimate of u cap v cap. Now the question is this: if I have an estimate like this, can I, using this estimate, take one of the frames, move it along this motion vector, obtain another hypothetical warped image where these two images are more nearby, and can I estimate the KLT once again? The idea is beautiful, but let's try to understand it better, seeing step by step. Therefore, what I'm saying is this: I am trying to obtain a vector, an image, after warping by using the first intensity based displacement estimate of the optic flow vector. Okay, then you can refine your estimate by repeating these steps. Okay, why do we do that? Please don't forget one important thing. Optic flow constraint equation was an approximation. We made a Taylor series expansion. After the Taylor series expansion, we just assume that everything is linear. And this is only true for small displacements. In other words, the function that we are approximating using a Taylor series, only around a small neighborhood, only around a small displacement, your linearization is correct. Therefore, Canada-Lucas tracker and the concepts based on optic flow constraint equation, that linear equation, can only be true if you have small intensity small displacement values. This is typically 1 pixel displacement, okay? But this is something very difficult to obtain. Now, how do we achieve this goal? Okay, we are talking about a refinement step, making an estimate of the optic flow, using this optical estimation, warping an image toward the displacement, obtain a hypothetical new image, and continue to estimate the optic flow. And we're saying that, hey, let's obtain small pixel displacements. One solution to small pixel displacement is image pyramids. Even you have a 1 million pixel image, if you have image pyramids getting smaller and smaller between two frames, you will have, in the lower resolutions, it will be very small, tiny images where the displacements could be very small. Okay, therefore you can make your KLT optic flow estimation at the coarser resolution and propagate the results to the finer resolutions. Therefore, without these two concepts, iterative refinement and image pyramid based optic flow estimation, we will not be able to obtain good results. Now let's see the details. How do we do that? Now let's see a very simple animation. Two frames. At x0, I'm trying to estimate the corresponding optic flow. This is a one-dimensional profile, please note. There is no y. Okay. Now, what we are doing here is basically the displacement that we are trying to estimate. It will be based on this slope. Okay, this slope here. This is special derivative with respect to horizontal. Okay, this is time derivative here, and what we are doing is we are just assuming initial guess is D0, we are trying to obtain an estimate, D cap, using the previous techniques that we have seen, okay? Therefore, I am estimating my new estimate as the displacement between these two things is equal to D1. Now, please note, D1 is not equal to this. Between two greens, it's not equal to D1. D1 is nothing but this little thing until the red uh, 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 tangential line. Okay, this is the due to linearization. You only estimate this thing. This is an error. Okay, therefore the trick here is this. But I made a correct estimation. If I use this estimation, I have to estimate the update, and I simply move. What I'm doing is, you see, f of x minus d1. I obtain a new image. That was my original image. This is my original image. That is my new image. How did I move? I moved using the estimate that I have obtained in the first step, named d1. I simply moved x point to d1 point. This is a simple translation. But now, if you go to the same point, if you take the very same linearization, nothing but this tangential line here, instead of this green to green distance, I can obtain red to green distance, and I'm gonna add as this du cap. This is my new estimate, and d2, my new estimate, will be the previous d1 times this d cap. Now, this is a much better displacement estimate. Now the things are getting nearer and nearer. My approximations becomes better, and at the end, as soon as you move f1, not d1 but d2, maybe both of these things will be on top of each other. This is the concept of iterative refinement. Without iterative refinement, the optic flow equation, the optic flow solutions will not work very well. We have to do it, okay? Now, this is the updated estimate, and you will obtain at the end maybe nothing but 0. Now, this is the pyramid we are talking about. Image J, image I, which is like T and T plus 1, 2 frames. This is the original images. You obtain smaller versions using simple decimation operations. Then you simply apply KLT using nothing but the upper resolution. Okay, with the upper resolution you are obtaining it, and then you will simply obtain an estimate like 1.25 pixels here for a pixel. Then you propagate your result. Since you are decimating by 2, we are going in this direction. Your estimate like 1.25 pixels, it will be 2.5 pixels prediction here, 5 pixel prediction here, 10 pixel prediction here. Therefore, your initial value, while you are trying to calculate an optic flow in this level, you will get your previous initial estimate, and you will warp your image using this estimate, and you will basically propagate the results to here as an initial estimate, and then you will solve optic flow just for the remaining part, which is the part which is not able to obtain through this prediction, and that part will be solved just like here as we did before. Okay, maybe this D1 is coming from the upper layer, and you are just solving for this displacement. Okay, now let's see the whole algorithm together. I know it's complicated looking, but it's a very important algorithm. It is the fundamental, like a benchmark algorithm for every vision scientist should know it very well. Right now, in this here, inside here, I am calculating the time derivative and horizontal derivative. This is our term, okay? This B vector is the term. This G inverse here is the famous 2 by 2 matrix we are calculating here. This is the special gradient matrix, Ix square, Iy square, Ix, Iy, within a neighborhood. I'm adding that. That's a 2 by 2. inverse times B is our OpticalFlow solution in the heart, in the center of the algorithm. But please note, I have to have two loops. One loop for iterative refinement, one loop for the image, the parameter that we have to have. This inner loop is iterative refinement. In other words, you just basically calculate you obtain this term, you add it on top of your previous estimate, you have a guess for the next iteration here. Okay? Now, this is the tricky part. Please note, I am taking my J image, I am using this estimate here and here, this estimate here and here, I am moving them, I am warping them as a new image. I calculate the time difference between two frames, one original frame, one warped frame, using this idea. You obtain the delta t here, which is used here as a time derivative, and we continue here in this way. Okay, this is until an accuracy is obtained, you continue like this. Now what is the other term? This is the other term is calculate. This is the loop that we have. This loop is we are calculating the obtaining the time derivatives and special derivatives with respect to your current scale, and here we are just multiplying by 2, okay, your estimates that you obtained, the final optical estimate at level L. Previously it was GL, you added on top of it, you multiply by 2. Now what you are saying is, this is my estimate for the next level. Maybe it is 1.25 here, you are sending to the next layer 2.5 displacement estimate, and everything starts from this 2.5, just like here, this 2.5 and this 2.5. This is the KLT tracker that we have, and that's one of the most fundamental important benchmarking optical flow equation solution, but only for sparse points, specifically on the corners. For edges and boundaries, your 2x2 matrix doesn't have an inverse, you cannot find it. On the corners, they work it very well. Now I'm gonna stop here. I'm gonna give a break. After the break, I'm gonna continue with the other algorithm.